Good morning, friends and colleagues. Thanks for the kind introduction. It's great to be here. Thanks for the invitation to this wonderful place I have very fond memories of, and to this wonderful workshop on algebraic structures in quantum computation, a heavy tool and heavy hammer, much to be used in the field for good reason, and we will come back to this later in the talk. Now, when I give talks, I usually try to be as faithful as I can to the overall theme of the workshop. That said, today will be a bit of a semi-exception in the sense that I will put a topic into the focus of this that is much inspired in mindset by algebraic methods and also by some of the techniques, but will not be fully spot on. And the reason for this is that I just felt like it. And I thought it would give rise to a kind of compelling story on the role of computationally bounded observers, quantum chaos, what we call pseudo-chaos from a quantum information perspective. That said, I will add two appendices or two addenda to be faithful to the theme on the growth of complexity, where semi-algebraic geometry methods come in, and a teaser at the very end on the classification of all Pauli Lie algebras. That, of course, is totally spot on for the workshop. The reason why I didn't put this into the center was, well, for one reason, that the most compelling applications just became clear a couple of days ago, and also the two PhD students involved are here, and I thought it would be nice to bring in a teaser and then let them add a lot of the meat and let them shine with the topic. And that's the plan for today. Very good. So, simulating quantum chaos without chaos. And here I give lots of credit to Lorenzo Leone on this topic, as I will explain it now. But let's start at the very beginning on computationally bounded observers, aka me, you, anybody with a classical computer. So let's assume I go into the lab. That was a joke. Never let a theorist into the lab. Somebody else goes into the lab and tries to find out some property of a physical system. And this experimentalist, or you, somebody else, goes there and say, given two quantum systems, given in some physical characteristic P, they aim at distinguishing between them, saying it's this or that based on data. So it's a very natural task. You go somewhere, want to find out what's going on in some lab in nature, and that's great. That's a very common task. But what if the time needed to accomplish this task is on par with the age of the universe? In what sense can we then speak of this being a physically meaningful property? And this is kind of the guiding question for the main part of this talk. In what sense we can think of a property here. So for now, we will call a computationally bounded observer, like someone like me, like you, anybody equipped with a classical computer, which would be an observer taking measurements and operating for a reasonable amount of time. aka, we are asking for this process to be sample efficient, like you take many samples, life is polytime, and you argue about this for a reasonable amount of time, aka a polynomially amount of time, as a statement on computational complexity. This is like basically everybody. Like whatever you do, you will take finitely many samples and will have many time. That's what you have in store. Let's make a test. There are two boxes with balls in them. Are the two boxes the same or different? Who thinks they are the same? Okay, who thinks they're different? Oh, it's kind of roughly 50-50. Okay, that's interesting. So you've done this, right? You've taken data, many data, and you've reasoned about this for a short time, and you've come to a conclusion. That's kind of the task that we have in mind here. And they're actually different. Here they are. They're slightly different, but, well, it takes some time to find out. Well, of course, such a task makes no sense for a given instance. As usual, you have to think about families of instance of a certain type, and you have to see how this scales with the system size. So the scaling with the system size matters, and if the problem size is n, an algorithm with time tau of n would be called efficient if this would be polynomial scaling in the number of steps in n and inefficient otherwise. This picture here is taken from the same course in cryptography, and it asks for the number of boxes that overlap and asks whether this is an even or an odd number. And again, if you look at the tiny instances, you can do this in your head to understand whether this is true or not. Like to the left, you stare at it, whether it's even or odd. But soon the probability of you guessing right will approach 1/2. That's amounting to equal guessing. Right? So this will be quickly converging to 1/2. So, warm up. The first warm up will be a tool that comes in quite a bit in this first part of the talk. That's related to pseudoentanglement. That's related to ensembles that look very much entangled, but in fact are not very much entangled. Yeah, this is kind of an interesting feature that this even exists. That's about ensembles or pairs of ensembles. On the one hand, you have like a pair of ensemble of pure states with the property that the entanglement would be close to maximal over many or the majority of cuts on the one hand, and another ensemble would be actually quite little entangled in the sense that the entanglement would grow like a small function, g of n, across the majority of cuts, and what you have available are polymany samples, and you have to be able to argue about them with polytime computations. And the point is that such pseudo-entangled states exist, which may be somewhat strange if you have not heard about this concept, in that there's families of states that for one ensemble is given by Haar random states, which have the property that if you draw them, that over all cuts they will be with high probability close to maximally entangled on the one hand, and on the other hand you have a family of states constructed in this way that would only grow logarithmically, and the way you construct them is that you have like a sum over subsets of all parties, and like -1 to some function f, a pseudo-random function f, and then if you take sub-ensembles, you will see that the entanglement of these ensembles is just logarithmically growing, whereas the Haar random has close to maximally entangled states with high probability. That said, you cannot discriminate one from the other. It looks highly entangled, but it isn't. Yeah, this is kind of there's cryptographic techniques coming in, so there's a lower bound and an upper bound, and this is kind of strikingly different in that the states look entangled, while in fact they are not. There's kind of cute properties that these pseudo-entangled states have. Here's one example of an unexpected feature that comes along here. This will relate to a paper that will actually come out tomorrow. It's already submitted. It will arrive on the archive, presumably tomorrow if it's accepted by the archive. And here's the thing, that's something that's made for Barbara Krauss, who's unfortunately not here today. Like the bread and butter, the presumably most celebrated result in entanglement theory is that there's, for pure state bipartite entanglement, one number to rule them all, as we know, in that there is asymptotic reversibility of entanglement manipulation. What does that mean? You have a reservoir of identically prepared states psi, and by local operations augmented by classical communication, ping pong, you want to transfer this reservoir of weakly entangled states to one where entanglement is present in a highly concentrated form. That's called entanglement distillation, that captures the resource character of entanglement. And the converse task is called formation, and the achievable rate is the so-called entanglement cost. And the big surprise value, or the surprise value a quarter of a century ago, was that this is actually asymptotically reversible in the sense that there's one number, and this is the one entropy, the von Neumann entropy of the reduction, and this gives rise to the rates of both processes. So even though you do measure and you're destructive, you're non-unitarily acting to the system, and it's of course not reversible, asymptotically it is reversible in that you can have weakly entangled states, you extract maximally entangled ones, you get weakly entangled states out again, and this is completely asymptotically reversible. There's one number, the one Renyi entropy that governs this all. Now, using pseudo-entangled states, you can construct other examples, and that's kind of challenging the view of this entanglement manipulation, because if we think about this, of course, all you could ever do is have many copies and operate in an efficient classical fashion. And that seems like a no-brainer. Of course, it's like that, but this was kind of overlooked in the old days when people looked at entanglement theory. You just have many copies and can do efficient computations. And what then turns out, if you require that quite naturally, well, quite obviously I would even say, then this can be vastly different. And if you think about computationally efficient steps of entanglement manipulation, there's family of states where this is vastly different in that the one process, the distillation process, goes like the min entropy, like the log of the operator norm of the reduction, whereas for the cost, you go like omega in n in the number of copies growing linearly in n. And that's just because you want to require this to be computationally ensemble efficient, which you naturally have to assume. So in this sense, entanglement theory was like incomplete because it was not accepting the obvious constraint of being efficient. Kind of funny. I find this paper cute because it connects like a more modern viewpoint on things with like the old stuff in entanglement theory, like the Barbara Krause of the world, and me did in PhD times, which is kind of cute. Okay, good. So pseudo-entanglement accepts that states can be very little entangled, although they look like highly entangled states. And again, it puts the observer into the center. You have to be sample efficient and computation efficient because that's all that I, you, everybody else has to his or her disposal. Sit-ups. Okay, here we go. Hamiltonian distinguishability. So we ask for Hamiltonians to be the same or different. What does that mean? Again, we take this observer-centric viewpoint. I mean, there's no point in a Hamiltonian being ontologically given. You take data and you learn a Hamiltonian from data. So what is reasonable access to an unknown Hamiltonian? I'm not making the same joke. Somebody goes into a lab and looks at a system and they will say, what is the Hamiltonian? Actually, we've been a lot thinking about Hamiltonian learning recently, and we calibrated the Google chip. There's a lot of interesting topics coming along with it because ultimately, like Schrödinger's equations even formulated the wrong way around because you have to know the Hamiltonian. Usually you do not know the Hamiltonian and you have to learn the Hamiltonian from data. So what you typically have is that you take data at different times and observe the system. That's what you have, right? So common access to an unknown Hamiltonian is that you let it go in time, evolve in time, and you would take snapshots in time. Yeah, that's a reasonable Hamiltonian access of an unknown Hamiltonian, or you would take the stage at different temperatures, different inverse temperatures, and probe thermal properties. In fact, again, in Hamiltonian learning, both the time-evolved states and thermal states are both discussed in the same way. And what we do is Hamiltonian access. Hamiltonian is black box Hamiltonian access if it can access the time evolution e to the power minus IH for any reasonable time, so polytime, as well as access to the Gibbs states for reasonably small temperatures. Again, if you have like a QMA hard Hamiltonian, then you would not require very low temperatures. I'm making the same point over and over again. Many samples, polytime, and that's all you have. So again, you would have polynomially many copies of that, and you would have a computationally indistinguishable physical system if you have two ensembles of Hamiltonians that are computationally indistinguishable if no efficient quantum algorithm can distinguish given black box Hamiltonian access to samples from the ensemble 1 or samples from E2, which means they are practically identical for anybody with reasonable resources. I make kind of the same point over and over again just to emphasize how natural it is, because life is finite, you are finite, I'm finite, labs are finite, you take data, and that's what you have in mind. What is quantum chaos? That brings us to the topic of the first part of the main part of the talk. And the answer is I don't know. I don't know what chaos is, right? I mean, we learned this in classical mechanics. Wow, that's like 101 classical mechanics stuff, that the system would be deterministically chaotic if you know this. Like if you're exponentially fragile to the initial condition, there's points arbitrarily close in phase space that would at later times diverge exponentially in time, which would be accommodate classically chaotic dynamics. Now, what is quantum chaos? And people fight and scream about this because, I mean, the obvious naive definitions will not work, but that's not a very deep insight. That the naive butterfly effect will not work in that you have states, like pure states that are very close to each other initially. They will be close to each other for all times because, well, scalar products are preserved under unitary dynamics, so they will remain close for all times. There's no naive butterfly effect in this sense. Not deep, but still true. Or asking for constants of motion, well, again, there's lots of constants of motion. In particular, if you have a many-body Hamiltonian, all the overlaps with the many-body eigenstates of the Hamiltonian will be preserved over time, and that makes 2 to the power of n constants of motion for every quantum system. So naive interpretations in terms of constants of motion will also not do the job. So we have to work a bit harder, and traditionally, a lot of the emphasis has been on spectral properties of Hamiltonians, where you say a Hamiltonian would be basically chaotic if the spectrum is kind of like a chaotic Hamiltonian. It's a very common type of reasoning. So we look for quantum systems with level statistics that are resembling classically chaotic systems. There's also a lot of work on semi-classical approaches, such as period orbit theory or decoherence. If they have a system and you couple it to environment and then you stare at phase-space pictures and you see that the phase-space pictures emerging are as if the system was classically chaotic. Also a big body of literature along these lines. You can push the system a bit and look at reactions to perturbations and so on. That's not uncommon. This is a bit like old-style quantum chaos, and in recent years there was a lot of pushing. No, I have one more thing to say about this, in that like spectral properties are usually captured in terms of like notions of like level spacing statistics. And if you look at the many-body eigenstates of Hamiltonian, of course there's exponentially many of them, and you look at the spacings of them, meaning the gaps between nearest energy values in the many-body system, you would crudely discriminate Wigner-Dyson statistics that's commonly associated with quantum chaos to Poisson statistics that is associated with integrable quantum systems. So Wigner-Dyson means that eigenvalues don't like each other and they repel each other. So the probability density to have a zero eigenvalue gap goes to 0, whereas for integrable systems, you have so many additional constraints and constants of motion that it's more like an IID type spectrum when you would have an energy density of the, or a probability density of the gaps being large at 0 value. So that's kind of the crude picture, Wigner-Dyson, quantum chaotic, Poisson-like, integrable. Yeah? So these things are very common and there's a huge consensus about them. They're not true in a mathematical sense as a theorem. There you can find integrable Wigner-Dyson distributed quantum systems providing counterexamples, but that does not make the overall intuition wrong. Seems fair to say. Now, recent years have seen a shift of emphasis, not so much to abstract properties of spectra or so, but put an emphasis to emergent properties of unitary dynamics that would capture physical features that could be observed, in the sense that if the Hamiltonian is chaotic, then the time evolution that you could possibly observe in the lab would exhibit quantum chaotic features in one way or the other. That's a kind of a more common way of thinking about quantum chaos in the way. You look at time evolutions, you say a system would be quantum chaotic if it behaves in a certain way. That makes also a lot of more sense from an operational perspective. And I will come to these properties in a minute. And before that, I say that the Gaussian unitary ensemble is indeed a system that has all these properties that I will name in a minute, the GUE. And that's kind of the plain vanilla setting of a quantum chaotic Hamiltonian. This we take for granted. I've made an experiment. I've statistically independently picked IID professors in condensed matter physics, and I have asked them whether GUE is quantum chaos, and they uniformly said, yes, that's what quantum chaos is about. I've made this experiment, and highly confidently I can claim it. Let's take this for granted. Okay, Henrik looks at me sharply, but I'm more serious about this than you think. So a GUE Hamiltonian is one where you have a unitarily invariant measure, like this one given here. It's characterized by Hamiltonians in the eigenbasis where you have eigenvectors. And because this measure is unitarily invariant, this measure will also be unitarily invariant. In other words, there would be H random. And the spectrum has the level repulsion built in that you want from Wigner-Dyson, so they don't like each other. That's the level repulsion put in, and that's what it is. So you have like U, D with the right diagonal, U star, U dagger, depending on your upbringing culture, U H random, and D is the diagonal that reflects the level repulsion. This is quantum chaos. Or this captures the properties of quantum chaos and features the quantum chaotic dynamics in the way I've advertised this. So here's properties that people would like to see. Say, if you have quantum information that's localized in some operator O1, localized somewhere in a many-body system, you say, if you let it go in time, how does that scramble and spread all over the place due to the quantum chaotic dynamics? And you would test this by a test operator O2 via the decay of the so-called out-of-time ordered correlation function, OTOC. That would be a key indicator of chaotic dynamics, where you say that this out-of-time ordered correlator with these funny times would be exponentially decaying in n, which would reflect a chaotic behavior. Or you can say you get like operator entanglement spreading, and the operator entanglement is just what you think it should be. You have a state that's the choice state of the observable in the Heisenberg picture applied to one part of a maximally entangled state. That's the choice state. And then you would like entanglement properties of this choice state. And if this entanglement is large, you would say it would be a quantum chaotic Hamiltonian in a way. So that's like OTOC is a key indicator. Operator entanglement spreading is a key indicator. That's how you commonly capture quantum chaotic dynamics. Again, there's counterexamples. I have stars. You can construct counterexamples. These are not mathematically rigorous statements, but most of the time you would see this as a natural property. Also, the states are complex and far from being classically simulatable for long times, in the sense that chaotic evolutions produce very entangled states at long times, so of the order omega n if they're chaotic, and so that quantum chaos would come along with high levels of entanglement along the way. So again, the Gaussian unitary ensemble paradigmatically fulfills those chaotic properties, kind of in line with the reasoning that GUE is reasonably capturing quantum chaos. It also reasonably features the dynamical properties that we want to see, OTOC scaling, operator entanglement spreading, large values of entanglement, and so on as features of quantum chaos. So these are probes to chaos. They're presumably necessary, but they are not sufficient for quantum chaos. So the modern approaches detect the presence from emergent physical phenomena, like, again, OTOC, entanglement scaling, operator entanglement. The last one is like related to magic. You can also make statements about that. I don't put this so much into the focus. But these are like dynamical features that you could observe. And then from these features that you observe, you would argue about the system being quantum chaotic or not. That's kind of a more modern viewpoint to quantum chaos after all. That's good. But then, to be fair, we have to put the observer into the focus. Right? I mean, taking this idea seriously, that you judge what quantum chaos is about by going to the lab, looking at the system and say, if it has that dynamical feature, I would argue about this. Then you say, good, but then be serious about the observer and be serious about an observer that's computationally bounded in the way as we've said it earlier, because anything else would be utterly unreasonable. Of course, this observer has poly resources, stares at the system, takes data, argues about this, and that's what is in store. And let's see what this means for our description of quantum chaos. So let's push the role of computationally bounded observers in quantum chaos and ask whether the following is possible. So that's a definition of a pseudochaotic Hamiltonian, which is again about two ensembles, E1 and E2. And so in one instance, you have an ensemble of chaotic Hamiltonians, which obey all the necessary properties of quantum chaos, and an ensemble of a pseudo-chaotic Hamiltonian that has two key properties. Property one is it's all wrong. It does not have any of the features you want to see. It does not exhibit chaotic properties. It has no level repulsion. The spectrum is wrong. The level repulsion is wrong. It has weak scrambling. That's also wrong. Low magic. I didn't speak about this. Low entanglement production. It's just not chaotic in any meaningful dynamical sense. Not. But it's not distinguishable from E to every computationally bounded efficient algorithm with Hamiltonian access. So it looks quantum chaotic. What? So this cannot exist. Right? I mean, if this existed, it would mean that all these necessary probes are actually not necessary. And quantum chaos can lead to the same emergent phenomena. You have like one Hamiltonian that's quantum chaotic in all the right sense, and another family of settings that are wrong in all possible ways, like level spacing, autalk, scrambling, entanglement scaling, all wrong. But operationally, by a computationally bounded observer, aka me, you, everybody else, looks quantum chaotic. That seems weird. So the core message, you can come back, is that this does exist. And that's the main part of the paper, that these settings do exist. So, reminder of GOE, we have said it before, or actually I pick up David's question. So the GOE Hamiltonians are of the form, the ensembles of Hamiltonians. Again, we are talking always about ensembles and about probabilities of being able to discriminate them as a statistical statement. U, D, U star, U is Haar random, D has the right spacing with a level repulsion, U star, that's what you have. That's the one Hamiltonian. It has level repulsion, fast and deep scrambling, high entanglement and magic with high probability, to come back to David's question, because as you are precisely right, it's about an ensemble statement. Now the technical part of this work is to spoof this and spoof eigenvalues and eigenvectors separately, and to prove that this spoofing cannot be detected. You will not be caught when you spoof. And the upshot of this is you take the eigenstates to be pseudo-random, but that look Haar random, but they're not. They're pseudo-random in the way I've explained earlier. And for the eigenvalues, you pick eigenvalues that are precisely right in the marginals. Because a moment of thought reveals that if you look at the individual eigenvalues of a Wigner-Dyson distributed setting, they would fulfill the celebrated Wigner semicircle law. And what we do is we pick individual eigenvalues, IID distributed, from the Wigner semicircle law. So the margins are right, but this level repulsion is completely wrong because that's IID, and you will see no level repulsion whatsoever. So that's just wrong, but the marginals are just right. That's our eigenvalue. You do U, D, U star, and U is Haar random. D has this completely funny, wrong level spacing, namely no repulsion, and that's what we do. That's our construction. And then we show that for any setting, polymany samples, polynomial computation, the ensemble is computationally indistinguishable from the Gaussian unitary ensemble given black box axis. And so it looks quantum chaotic and it isn't. So let's meditate a bit about this, because I must admit, I mean, this is a theorem, so it speaks for itself, but I still have not made quite peace with that. So if we look at the settings, the pseudo-GOE and the GOE, in one case you have no level repulsion because you've picked eigenvalues IID. By construction, there's no level repulsion. It's one of the defining features of GOE to have level repulsion. It's inbuilt by its very construction. Autocs are saturating at levels here. That's completely wrong for long times. The saturation value of the out of time or correlation functions is wrong for our ensemble. But to see this, you have to go to too long times. You've died before when you see the point when it's different. But the asymptotics is vastly different. Deep scrambling has this 1 over omega e to the power n. You look at the entanglement, 1 is very high, that is bread and butter. I think everybody in the room knows how to operate these Levy's lemma type techniques to show, this how most say it's standard of entanglement. Here, you have very little entanglement. So the order polylog n in time, in the two-Arrhenius entropy, it's very little entanglement. That's why it's also wrong. But you cannot discriminate that. This is what this is about. So you must be joking. Well, yes, no, I mean, it's a theorem just for yourself. So let's look at the number of applications. So there's a number of cute features on top. One thing is that this is not only a fake ensemble that's operationally indistinguishable from a quantum chaotic one, but it's also efficiently quantum simulatable. You can run this on a quantum computer while you cannot realize quantum chaos on a quantum computer. So the GOE suffers from exponential quantum gate complexity. That's kind of clear because far random states are already very costly, as we know. This you can do, so you can run this on a quantum computer. There's a big appendix on having a quantum simulation algorithm running this on a quantum computer. They're statistically far, but computationally close in a way, if you want. It also means, as a corollary, this is a short paper and has like infinite appendices. So for each of these statements, there's a long appendix. There's no experimental method to detect Wigner-Dyson from Poisson statistics. Obviously, because if you could do this, this would be a test for our discrimination, and that would falsify our statement. It cannot. It's kind of weird. You cannot discriminate Wigner-Dyson from Poisson operationally ever, from polynomial bounded observers, which is strange. Actually, I didn't know before that, but it's interesting. So it's obvious by construction now. This no-go theorem even holds for Hamiltonians that are highly structured. You can even assume this to be sparse on the computational basis, and this would still be true. Yeah, the sparsity doesn't help. It's like weird. It is what it is. It also gives sample complexity lower bounds for scrambling property testing. So given Hamiltonian in time, this autoc to be larger than k requires 1 over square root of k access to h in this way of Hamiltonian access I've explained earlier. So you also get a lower bound of a sample complexity for testing certain scrambling properties. What does this all mean? Honestly, I don't know. And maybe that's the reason why I give this talk, because I don't know what to do with this. It's like you have a system that's quantum efficiently simulatable. It's just not quantum chaotic. It has the wrong spectrum, the wrong eigenvalues. It doesn't have the right scaling of the autocs, the wrong scrambling. It's all wrong, but it's operational, not discriminatable from the true thing. It's a bit like I say that the sky is blue. Actually, it's quite nice today. So yeah, judge for yourself. You are making this observation, look at data, and you judge. But say, if you look at the sky, and from many samples and efficient computation in your head or in your iPhone, in your computer, you cannot judge whether the sky is blue or red. What does it even mean for the sky to be blue? Right? I mean, it challenges what it means to have a physical property if from many resources, which is all we ever have ever, you cannot make that distinction. It's like that. And that's the point of the first part of the talk. Here, in short, linearly growing complexity. Of course, these are topics that would deserve long talks in their own right. It would be a bit superficial, but I throw them in, and then we can maybe talk about them. So this question has to do with the growth of complexity for random quantum circuits. You take a random circuit, say a bricklayer or something, you pick how random gates, and you say, how does the complexity of the circuit grow with the depth of the circuit? Now the circuit complexity would be, for a given gate set, the number of gates you need to either exactly, that would be the exact gate complexity, or approximately, say, the operator norm sense, recover the full unitary. So given a unitary, you want to decompose the unitary into certain gates, and the number of gates you need would be the circuit complexity. That's obviously related to computational complexity, and that stated that this high complexity is like highly complex in a precise way I'm happy to explain. It also relates to phases of matter in the sense that you would, as David here, if you would think that a system would be in the same phase, if you can go from one state to the other with a with a constant depth quantum circuit and so on, in condensed matter is very important, but it's also computationally hard. I mean, it's not very surprising. You have notorious cancellation, you build up entanglement, then you undo stuff in later times, you build something again. There are certain variants of the problem that are proven to be hard, say the T-count problem. If you decompose the unitary in Cliffords and T-gates to decide whether you need more or fewer than T-gates is not possible in polytime unless P is NP. So these are always hard problems. The gate decomposition problem, that's not easy. So if you have a random circuit, how does the complexity of the circuit grow with the depth of the circuit? Of course, every circuit is its own description. The point is, can you compress it and find a shorter description of the same circuit for the same unitary? That's the question. And this has risen to prominence for these flamboyant figures, Brown and Susskind, who have made the point in the Brown-Susskind conjecture relating this to the ADS-CFT correspondence. Don't get me going, it's a correspondence between Einstein gravity in a negatively curved bulk where there's a CFT, a conformal field theory, sitting on the boundary, and it's a duality between ADS, Einstein gravity, and the conformal field theory on the boundary. And they've been meditating about thermal field doubles and the growth of the volume of wormholes in such a setting here on the gravitational side, and they observed, or they discussed, that the volume would grow for an exponentially long time, and there must be something on the quantum side that would resemble this exponentially long linear growth in time. And they said, what could be this quantity? Maybe it's the complexity of the state that would do that. And through this connection, this question kind of rose to prominence in that you have like linearly growing complexity until exponentially long time. But how would you judge? You get these cancellations. This was an open problem for long. So I throw in some techniques that are nice in this context. What we did, I'm happy to say more. Indeed, the linear growth conjecture is provably true by accepting that you have some choice of unitary gates and you place them on the circuit, and no matter what you do, we'll get some reachable set, very fingery reachable set of the image of this UA. It's not a manifold, but it's some reachable set of some dimension. It's the unitaries you can generate by placing the unitaries. There's a kind of dimension of this. There's like that's kind of the beast that we use to tackle the problem. And the key insight is that this set is not a manifold, but it's what it's called a semi-algebraic set. So a set that is constrained by polynomial inequalities and equalities. Take like the unit disk in 2D. That's not a manifold, but the circle is a manifold, and the open boundary disk is also a manifold of dimension 2. This accessible dimension is like the largest dimension of a manifold in this foliation of the semi-algebraic set in terms of manifolds. And the heavy lifting is done by what is called the Tarski-Seidenberg principle that tells us that if you map a semi-algebraic set to something by a polynomial function, you will again get a semi-algebraic set. And then you meditate about this and find that this does a lot of the heavy lifting, because if you look at the contraction map, like the implementation map, and look at the linear approximation of this around a point, you see that almost all points will have the maximum dimension. And this puts the problem upside down in the sense that you don't have to optimize over all circuits and all settings, but generic circuits will have the generic feature of the dimension growth that you have. That's kind of the flipping point. And then you have to find some circuit that has the right feature, and much of the paper does the nitty-gritty work on doing this for Clifford circuits, where you do random directions and push the Paulis through the Clifford circuit. That's painful, but then you see that you get the right dimension with this random Clifford circuit, and you indeed find the linear growth conjecture is provably true for until you get an exponentially large time, like 4 to the power of n or so. So the circuit complexity is lower bounded by this number here. That's exponential. That's linear in m in the depth until an exponential depth in both n and m. So the linear growth conjecture is true. I'm saying this for a couple of reasons. One thing is that it solves this Brown-Susskind conjecture. This is not robust. We did this for the exact circuit complexity, but this can be made robust if you want to have an approximate complexity. This also works up to small operator norm error. There's cute physical insights because like notions of thermodynamics are nicely made reasonable. You find kind of cute trade-offs, say in Landau erasure, because if you accept that every process in nature will be finite in circuit complexity, you see interesting consequences for thermodynamic processes that come from constraints on circuit complexity. There's also relationships to entanglement that I'm happy to explain. Last addendum, which is a teaser to basically tease the gentlemen in the back, Simon and Gerard, who have a poster. So I tease this project on a classification of all Pauli Lie algebras. Here are the people who are here. So we don't need to be reminded what a Lie algebra is. It's a vector space over some field and a Lie product, under which is closed, that satisfies the common conditions of bilinearity, antisymmetry, and the Jacobi identity. And it's helpful and important to have characterization methods for a given set of generators to capture the Lie algebras that come out of this. Obviously, it's extremely important quantum control. Like we have a gentleman in the first row that has done a lot of work in this respect. It's much discussed in the quantum machine learning context, also in notions of Barron plateaus and trainability of quantum circuits, and also in notions of classical simulatability of quantum circuits, where these ideas come in. So what we did is to look at an important toy setting where the characterization of Lie algebras can be completely settled in all generality, namely the setting that is generated by an arbitrary set of Paulis, where this is the Pauli Lie algebra with this being the standard commutator setting. That's clearly important in variation quantum circuits, classical simulation methods, like tools to classically efficiently simulate quantum many-body systems, in measurement-based quantum computing that relates to much of Robert's work, to product formulas in quantum simulation or classical simulation, quantum simulation methods of quantum many-body Hamiltonians and all that. And what we do, and that's what the poster is about, is we provide a complete classification and also a characterization and a code for all such G. And the upshot of the proof on the core idea of this is to map the problem to a graph problem, namely a graph that reflects anti-commutation of the Paulis, accepting that Paulis either commute or anti-commute. So this graph would capture the anti-commutation properties of the setting. And then much of the argument argues around certain graph operations that would keep the Lie algebra invariant, but would change the graph as a sequence of graph operations that are like conditional local complementations, much related to the problem that Robert and myself and others have looked at some time ago when you manipulate graph states under local Clifford operations. And then you formulate a graph reduction theorem, and indeed, doing that, you can provide a complete classification and characterization of all such G. And the outcome is somewhat surprising in that there's not so many classes. There's, if you think about Clifford inequivalent Pauli Lie algebra, so you look at the orbit of the setting under Clifford's, you find there's only 6 Clifford inequivalent classes. equipped with a simple set of canonical operators for each of them. And they're all exponential in size except the Majorana free fermionic Lie algebra. That has polydimension and the others are exponential. So in a way, Majorana fermions are all there is and the other Lie algebras are large. And the poster by Simon and Gerard is precisely about that. So I very much advertise to go here. Which brings me to the end of the talk and the coda of all this. So in this talk, we have done something very natural. And I've just said whatever you do in nature, when you observe nature, when you look at the sky, when you go to the lab, you will be mildly constrained in your resources. You will have many samples. You will have a classical computer in your lab. There's nothing you can ever do about anything in nature with super polynomial resources. Well, it's a kind of an absolute no-brainer. Of course, we only have polynomial resources. But this has been somewhat not overlooked, but not sufficiently appreciated that this is all you have. And we looked at what it means to have computationally bounded observers. And this kind of introduced a new perspective in physics, where the observer is not just a verifier of a quantum theory that's existing beforehand, but has an integral part of the theory itself, because if you have a quantum chaotic system or not, if this cannot be discriminated by someone who has reasonable capabilities and resources or access to resources, then what does it mean to have that property? So this is what this challenges. What does it mean to have a property if you cannot efficiently detect that or argue about this? So this kind of challenges that quantum chaos or the necessary conditions defined for quantum chaos are even meaningful, because if you have them or not, cannot be operationally discriminated. I think I've made my point. I find that strange because it tells us that the way we think about quantum chaos makes no sense in this sense. There's lots of open questions that come along with this. We are thinking about thermalization, local pseudochaotic Hamiltonians, because the ones that we have now are not geometrically local. It's an interesting set of questions. And what does it all mean? Of course, you can think more along these lines, what it means to have computationally bounded observers and what this means for observing nature altogether. Because I do insist that we should think about computationally bounded observers, because anything else makes no sense to me. I'm pretty convinced about this. Then I added, as a sneak preview, two little appendices. We revisited the linear growth of the quantum complexity of random quantum circuits. That was an acute mathematical statement. Of course, there's lots of open questions. In particular, this kind of proxy setting of random circuits was, of course, chosen to have a mathematically reasonable proxy for the real thing of quantum chaotic dynamics. But that begs for an answer to the question, right, but what happens if you have an actually quantum chaotic Hamiltonian, say with trotterized dynamics? What does the complexity do then? And then you have to think harder about how to tackle the problem, because naively you get a jump from 0 to exponentially large complexity. You have to work harder to make this meaningful for natural Hamiltonians. In the very end, I advertised the poster by the two gentlemen in the back on the full classification of Pauli Lie algebras, and I advertised the poster. I also advertised new insights on a harvesting of this new classic of all this in new classical simulation methods for quantum systems. And on that note, I thank you very much for your attention. I'm looking forward to questions you might possibly have. Thank you.